Up till now we saw how to do analysis of algorithms which is independent of the implementation details. We also saw how to represent data in machines by looking at few of data structures. Data structures mainly were categorized into two parts: linear data structures, in which data had no relationships in between each other, and we looked at nonlinear data structures which were represented using trees, which had relationship between the data elements. That relationship was caught by the parent-child relationships. With this, now we come to the first application and try to look at the various algorithms to do this application. The application is the sorting application which we come across in our daily usage. A lot of time when we want to, given our data, we want to put them in some order, either increasing order or decreasing order, so that access is fast, the querying is fast, and quite a few other things. So that is the first application that we are going to look at, is the sorting application. Precisely to define the sorting problem, we are given a sequence of numbers and we want to arrange or rearrange them, or we want to find a permutation of these numbers such that this permutation or the rearrangement is in increasing order. We will see that this particular problem has many solutions. We will try to analyze them and try to see under which conditions which of the solution is going to be better. The first solution that we look at is what is called the insertion sort algorithm. This algorithm works on the principle that we use while playing cards. While playing cards, when we want to arrange the cards in our hand, we pick them up from the table one by one, and as we pick them, we keep on arranging them in our hand. So, I can visualize this as you have cards on your table, you pick up the first card, keep it in your left hand. Now, this card, the single card, is in its right position. Now, you pick up the second card, keep it in the right position relative to the first card which is in your hand, and you keep on repeating this process until there are no more cards that to be picked and arranged. So, this is something that we do naturally when we play cards. The insertion sort algorithm is simply going to abstract this principle and use it to sort a given sequence of numbers. So, let us try to see what we do when we say that we are putting the card in its right position. So, as we pick up, so suppose we have in hand already cards with these numbers. So, we already have picked up first the 2, then 5 and then 8 and put them in the right order. Now, as we pick up the next card from the table, which is say 6, we want to put this in the right position in the sorted list. So, what we do is we compare it with the rightmost element, which is the max element of the card which are already sorted. If it is bigger than that, there is no need to compare it with the rest of the elements on the left. We can immediately put it after that element. If not so, we know 6, we are going to compare with 8, we know 6 is less than 8. So, to find its correct position, we compare it to the element which is to the left of 8, which is 5. So, next you compare 6 with 5, we know 6 is bigger than 5. So, we know we are going to place this between 5 and 8. So, when we say we put it in the right position, we are precisely doing this sequence of comparisons. The key observation that we do or we naturally do is in practice is the cards that which already in your hand or the sequence that is you already seen is already sorted. So, that is a key observation which is important in placing this in a correct order. So, just to put things in a stepwise manner, we start with a singleton list, that is a single element. We repeatedly insert elements one at a time while keeping it the sequence sorted. So, initially we will have A1 in your hand, which is already in a correct position, then we will pick up the second element and insert it in the right position. So, we already have a sorted part of 2 elements now. Then we insert a third element and we have a sorted list of 3 elements. So, this is a incremental way of doing things. At every step, when you insert an element, you insert so that you have a sorted list in your hand. That is, at ith stage, after you insert ith element in the right position, what we have is a sequence of I numbers which are in increasing order. Let us illustrate this with a simple example. So, the sequence that we are trying to sort is 5, 2, 4, 6, 1, 3. So, we start with 5 in our hand, that is one element which is x, which is A1. Then we pick up 2. Now, 2 to put right position, we are going to compare it with 5. It is less than 5, so I am going to put this here. So, what you have now is 2 to 5, which is a sorted list. Now, you pick up next number, which is 4. Okay, so, as you pick up 4, we will compare it with 5, less than 5. So, compare it with the element which is to the left, bigger than that. So, you are going to put 4 here, and that is what you have here. So, we keep on doing this process until there are no more elements to be inserted. At that particular stage, you will have a sorted sequence. So, that is a simple algorithm to insert elements in a already sorted list. This is the pseudocode notation for insertion sort algorithm. Right? Your loop is starting from I equal to 2. This is because you already have A1 in your hand, which is in its correct position. So, you pick up the next element, which is I equal to 2, you assign it to the variable key. Now, you are going to, this part is going to insert AI into the sorted sequence A1 to AI minus 1. So, when you pick up AI, we know that already A1 to AI minus 1 is in a correct order or is in sorted fashion. So, this part is simply going to put AI in its right position. If you look at the algorithm, you have if conditions. So, if while or whatever you have, and so this is AJ is, if AJ is less than key, you are going to do something. So, this naturally gives rise to 2 ways of analyzing the algorithm, that is the best case analysis and the worst case analysis. So, we are going to do the best case and the worst case. Worst case analysis we already know is something that we can guarantee that whatever your input is, if you do this many computations, then you are going to get a sorted sequence. Best case happens only if you have a particular instance of a problem. So, in practice, usually worst case analysis is more useful than the best case analysis, but wherever possible or a point is to be noted, we are going to do both best case and the worst case analysis. So, let us try to look at the example and try to guess or try to understand what this best case and worst case are going to be. So, I am going to look back at the same example and try to see what exactly is going to amount to the best and the worst cases. Now, if I look at this particular step, when you have already 2, 4, 5, correct. So, you already have 2, 4, 5 in your sorted list and you are trying to insert 6 into the sorted list. Now, as you try to insert 6 into the sorted list, you are going to compare it with the rightmost element, which in this case is 5. As soon as we observe that 6 is bigger than 5, there is no need to compare it with the elements to the left of 5. We can as straight place it after 5. Right. So, what we see is that to place 6 in the right order or in the right position, we need only one comparison. Right. So, that is the best case of your algorithm. That is, as you try to insert an element, you can insert it in the right position by just making one comparison, and that case will happen if the element that you are trying to insert is going to be bigger than the maximum element or the rightmost element of your list. So, if I look at this process of inserting n elements, so let us try to extend this to n element argument. So, if I have a sequence which is like 1, 2, 8 and 9. Now, every time you try to insert, say you start with 1 initially, now you try to insert 2, we know 2 is bigger than 1. So, you need to do only one comparison here. Then you try to insert 8, 8 is bigger than 2. So, we can easily decide the position of 8, which is here, and you need only one comparison, and similarly about 9, you need one comparison. So, the total number of comparisons is 3. So, if n is the number of elements in your sequence and you are trying to insert n minus 1 elements, for each element the best case is going to be that its position to be decided requires only one comparison. Right. So, this is if n is the number of elements, which is 4, then this is n minus 1, and this is the best case of your algorithm. So, the best case, in the best case, if there are n elements, you need to do n minus 1 comparisons, and your best case instance is a sequence which is already in increasing order, correct. So, if I look at this, this is a sequence which is already sorted and you are trying to sort it. So, this is the best case analysis of your algorithm. So, if you look at now the best case occurs when the list is already sorted, and in this case you require n minus 1 comparisons, that means it is of order n. So, it is an order n complexity. So, that is the best case of your algorithm. Now, let us try to imagine what the worst case analysis is going to be. So, let us try to look at this particular case in this algorithm. So, I am trying to look at a intermediate step in your algorithm when you have 2, 4, 5, 6 in your hand, that is already sorted, and you are trying to insert 1. To insert 1, you will start comparing it with the rightmost element, less than the rightmost element. So, move to left, which is 5, less than 5, move to left, 4, less than 4, move, and less than 2. So, move to right, to the left. So, and you are going to put here. So, the number of comparisons that you are going to do is 1 here, 2 here, I mean this is one comparison, this is comparison, this is comparison. So, total number of comparisons is 4. So, if I have 4 elements, to decide the right position for 1, you need 4 comparisons. That is, to insert ith element, the maximum number of comparisons to decide its position will be I, and you can extend this now to a general case of n elements. So, let me look at the sequence which is like 8, 6, 4, 2. Okay, so, we will insert 8 first. To insert 6, you are going to as you try to insert 6, you are going to compare it with 8 and you are going to put it here. So, this will give me one comparison. Now, as I try to insert 4, you will compare it with 8, compare it with 6 and decide to put it here, and this would require 2 such comparisons, and for 2 you will compare with 8, 6 and 4. So, you will get 2 here, and that will require 3 comparisons, and that is what we observed. If at ith stage you want to insert, in the worst case you have to do I comparisons. So, the total number of comparisons is going to be sum of this, which is 6. Right. Now, this again let us try to abstract to a general formula. So, this is the worst case. So, if T n represent the time taken to sort n numbers, then this is going to be actually in the worst case equal to. So, for inserting first element 1 comparison, second 2, ith will be I, and for the last element it will be n minus 1. So, the sum of the first n minus 1 numbers, which is n into n minus 1 by 2, which is of order n squared, right. So, you can see that the best case and worst case vary by a large amount. The best case is linear with respect to n, whereas the worst case is quadratic with respect to n. Many times we also would like to know what happens in average or for random inputs. What we have seen is the best case and the worst case, which are always rare in applications. Mostly you deal with random inputs. So, how does algorithm compare or behaves when we have a random input? So, that precisely is given by what is called average case analysis. Wherever possible and easy, we will try to work out the average case analysis. Otherwise, we always would try to find the worst case of an algorithm. So, for an average case analysis, we assume that all possible permutations of the keys are equally likely, and with this we try to find the running time of the algorithm. To make things simpler, to make the analysis simpler, we will assume that we have a sequence of distinct keys. What can be shown is that this really does not restrict the analysis to the general case. So, what we will try to determine is what is the average number of comparisons that you need to do to insert an element into a sorted list. So, let us try to look at the ith iteration, or when we want to insert the ith element into a inserted list, into a sorted list. Now, we know you already have 1, 2, 3. So, I minus 1 elements are already in a sorted manner. Now, you are trying to insert the ith element. Now, there are I possible positions that this can go to, correct. If it is bigger, it will go here. If it is less, it can go here, or it can go here, or at the most it can go here, correct. So, there are I possible positions. For example, if my keys were say 2, 4 and 8, and the next key was say 9, then it could have gone here. If it was 6, it could go here. If it was 3, it could go here. If it was 1, it could have gone here, correct. So, if I am looking at I equal to 4, it precisely has 1 position, 2, 3, 4. So, it could go to any one of these 4 positions. So, there are I possible positions, and when we say all possible inputs have an equal probability, that means there is an equal chance that it could go to any one of these I locations, correct. That means given randomness, all these I positions are equally likely to occur. So, using this fact, the average number of comparisons that we need is, so this is j equal to 1 to I minus 1, this is j, and the probability that for j you have j possibilities and each has an equal probability to occur. So, I am going to divide by I, plus I am going to have I minus 1 to I, this is for the position 0th position. This is sum of the first I elements, I minus 1 elements. So, you will get this as I into I minus 1 by 2, and I will cancel out. So, I will get I minus 1 by 2 plus I minus 1 upon I. This is for the ith element. Now, your I varies from 1 to or to n minus 1. So, you are summing this from I equal to 1 to n minus 1 to get the final average number of comparisons, which works out to be the following number. Now, we use a well known equality from school algebra, in which summation 1 upon I, the first of the sum of the first n reciprocals is log n. Using this fact, we prove that the total number of comparisons in average needed are of order n squared. So, what we observe here is that on average your algorithm behaves like the worst case of the algorithm, whereas the best case is linear in n. Right. So, we have looked at insertion sort in a complete detail. We have seen the best, worst and average. So, that average case in insertion sort behaves like the worst case. So, probably the algorithm is not good enough because your random cases behave as the worst cases. So, let us try to see if we can have some other solution to the problem. That brings us to the next algorithm, which is called a merge sort algorithm. In this particular algorithm, given an element sequence that we want to sort, we divide this sequence into two subparts n by 2 of size n by 2 each. Okay, so, we are going to break them into two sequences of size n by 2 each. So, if I look at this, if I have a given sequence, I am going to break it into two parts, right. So, the given sequence you are breaking into two parts. So, this has size n, this has size n by 2 and this also has size n by 2. Now, we use the same procedure at this particular two shorter or smaller sublists. So, we sort the two subsequences recursively using merge sort. That means, we keep on dividing them into half until we have one element sequences which we know is already sorted. Finally, once we have this as sorted sequence and this sorted sequence, we try to merge them into a single sorted sequence. Okay, so, the general algorithm is find the mid position of the list, merge sort the first sublist, merge sort the second sublist and merge the first sublist with the second sublist. So, that is the idea of a merge sort algorithm. Let us see this by an illustration, that should make things clear. So, we have a sequence which we want to sort. So, as the first step of merge sort algorithm, we are going to split it into two sequences of size n by 2 each. So, I have a size, so this was 8, we have split this into two halves, one each is having this. So, this is my list 1, this is my list 2. Now, we recursively apply merge sort to list 1 and then to list 2. Recursively applying would mean you will split this again into two halves, split this again into two halves. At this level, you have one element sequences which are already sorted. Okay, so, first you will apply to L1, reach this position, then you will move to L2, you are going to apply it here and you get this list, and at this juncture all your elements are single, all your sequences are single element sequences. So, they are sorted, they are already sorted. So, that brings us to this. So, what we have done is we have merged sort. So, we have broken up to the leaf level where each of them sequence has exactly one element each. Now, after this we start the merging process. So, we merge this two into a single sorted list. Similarly, we combine this two and find this sorted list. Similarly, this is going to be this and this, correct. So, what we have done is we have taken all such two element things now, merge them into a two element sorted sequence, and now we continue this process. At the second stage, we combine this two and this two to get this list and this list. Now, if I look at this list, this is L1 sorted, correct. This is L1 in a sorted manner and this is L2 in sorted manner. So, this precisely is the state that is mentioned here. So, this is after doing all this particular procedure, we will have L1 and L2 which are already sorted. What remains is to do is the merge of the first sublist with the second sublist, which is done in this. So, you have this sorted, which is L1 sorted, this is L2 sorted, you have merged it into a single sorted list. Right. So, the procedure is easy to understand. Keep on dividing into half until you reach one element sequences, which then we know are already sorted because they are one element sequences. From this one element sequences combined to form two element sorted sequences. Using such two element sorted sequences, go to 4 and keep on doing until you get the original sequence in a sorted manner. Let us see how we are going to merge two sorted lists into a single list. So, let me look at two lists here. We will see how we are going to try to merge them into a single sorted list. The merge procedure is as follows. We are going to repeatedly compare elements of L1 with elements of L2 and copy the smaller element in L3, correct. So, given L1 and L2 will form a size list or array of size double of L1, call it L3 and store the elements there, correct. So, let me illustrate this merging procedure with an example. These are the two lists that we have. We are going to point markers. So, I have L1 and L2. So, initially I and j are both pointing to 1. Now, we will compare L1 1, correct. So, we are going to compare L1 1 and L2 1. As we compare, we see that 2 and 5, 2 is less than 5. So, the smaller one we copy in L3 and you increment, we already seen this. So, you increment I to here, okay. So, I has moved here after the first step. Now, we will compare and j is still pointing to the same old location. So, now you are going to compare these two elements and continue the process. So, let us see what happens. So, as you compare now 7 and 5, we know 5 is smaller. So, you are going to put 5 here and your j now will move here. I is going to point to the same index. Now, we will compare 7 and 20 and we see that 7 is smaller than 20. So, you will put 7 here and you will increment I here. J is still pointing to 20. You will keep on doing this until you exhaust both the lists, and what you will have here finally is a sorted list. Okay. Let us try to look at running time for the merge sort algorithm. So, if you have T n is the worst case running time to merge sort n numbers, then if you look at the algorithm, let us go back to the illustration of the algorithm. So, if the time required to sort this element is T n, right, n is the sequence of elements that we want to start, T n represents the time required, then this time required is going to be same as time required to sort this sequence which is of size n by 2 plus time required to sort this sequence which is of time T n by 2. So, as I sort this, you are going to return these two elements. So, T n by 2 will mean the time required to sort the list of size n by 2, which is going to be this process, it is T n by 2. So, T n, if I look at now T n, this will be T n by 2 from this part, T n by 2 from this part, right. So, you have 2 T n by 2s which will give me this stage, and what you require is time required to do the merge plus the time required to do the merge, correct. So, the time required to sort n elements can be represented using time required to sort n by 2 elements plus time required to merge the two things into a single sorted list. Now, if you look at time required to merge the two sorted lists, let us look at this particular example. So, the time worst case to require merge is going to be, so you are going to start with I equal to j, I equal to 1 here and j equal to 1. To completely fill up this list, I has to go from 1 to, correct. So, I has to go from 1 to n by 2. Similarly, j has to go from 1 to n by 2. So, in the worst case for merge, you will require n by 2 plus n by 2 comparisons, that is equal to n comparisons. So, the merge process will require n comparisons. In practice, it might require less number of comparisons. For example, if I look at the following example, let us try to look at this example and try to finish this process. So, we started with 2, then we will have 5 we saw, then we will put 7, then we will put 20, sorry. So, you will put 5, then 7, then you will compare 16 and 20, you will put 16, then you have 35 and 20, so you will put 20, then you have 35 and 25, so you will put 25, then you will have 35, and then this list is exhausted. There are no more elements from this list which has to be inserted into L3. Now, these two elements can be inserted without doing any comparisons. We simply append them here, correct. So, for inserting these two elements, we do not need to do any comparisons, right. So, though the worst case of merging procedure will take n time, it can happen that with less number of computations or less number of comparisons than n, we can still achieve the merging. It is a good exercise to write down the best case and the worst case instances for merging process and try to understand the merging process. So, what do I get here is the following. So, I have T n is equal to 2 T n by 2, here you already seen this factor comes from T n by 2 twice, plus n is the time required to merge. The base condition is T 1, that is already of constant time, which is 1. Now, this recurrence relation can be solved by using substitution method. So, I have T n is equal to this, you keep on substituting the same equation for T n by 2. So, instead of T n by 2, correct, so for this I know T n by 2 is going to be equal to 2 T n by 4 plus n by 2. So, instead of 2 T n by 2, you are going to put this particular thing, and you keep on doing this until you have here n upon 2 power k, which is 1. Let us assume for simplicity that we are doing analysis for n equal to 2 power k. Once you do this, we can easily extend it to a general case when n is not a power of 2. At this particular stage, you get this as order n plus n log n, which is of order n log n. Okay, so, we have done this analysis for a particular case which allows us to minimize our algebraic computations, but it can be shown that this can be then extended to a general case when n is not a power of 2. So, what we observe is that the running time analysis is order n log n. Now, what can be observed, not difficult to do, is that this happens to be the best, worst and the average of case for the merge sort algorithm, that whether you have sequence which is already sorted or sequence which is in reverse order or a random sequence, the complexity does not change, unlike insertion sort where in the best case it was n and in worst and average case it was n squared. That is an exercise which can be worked out easily and observed. The merge sort algorithm that we did also is a special case of a very popular design strategy, which is called divide and conquer strategy. Right? Divide step we already know, we kept on dividing until we have single element lists. So, that is the divide stage. The conquer stage is when we had two sorted lists, we merge them into a single sorted list. So, we have a divide and conquer design strategy. This is a strategy which is going to be useful in doing many applications. This is something that we do a lot in practice. When we are asked to solve a large problem, we tend to see if we can do smaller sub problems easily, and then using the solutions of these smaller subproblems, try to solve the original large problem. And that is a very useful strategy that is going to be employed many a times. So, in the divide stage, you divide that input into, in practice, more than 2 parts. In merge sort, we did exactly in 2 parts. We will see applications where we need to divide into more than 2 parts. Then we recursively solve those subparts. So, we are going to solve all the subproblems recursively, and the final stage is concur, where the solutions of all the subproblems are merged into a solution to a original problem. The analysis of such algorithms, which uses design strategy of divide and conquer, can be done via recurrence relations. So, I am just looking at merge sort in the preview of divide and conquer strategy. So, in merge sort, the divide part was to divide it into 2 parts, S1 and S2. The recur part was to sort S1 and S2 using merge sort, and the conquer part was, once S1 and S2 are sorted, merge them into a single sorted list. Okay. So, merge sort algorithm precisely follows the divide and conquer strategy. In general, wherever we are going to use divide and conquer strategy, the analysis of the algorithm will be done via using a recurrence relation. Many times the recurrence relation is going to have this form. This is the time, a constant time is needed to solve a problem of say fixed size. In terms of sorting, we saw that if you have one element sequence, it is already sorted. Okay. So, the time required is constant time. In practice, it may not be n equal to 1, it can be some n equal to d, and then we know the time taken is some constant. This term comes from the fact that you have a subproblems, correct. So, if you recollect, I can write T n as 2 T n by 2. So, in this case, 2 were the number of subproblems and n by 2 was the size of the subproblems. So, in practice, in general, you can have a subproblems, each of size n by b, correct. So, this indicates you have a subproblems that you have to solve. The size of each subproblem is n by b. This factor is the time required to finally combine the solutions of this a subproblems into a solution to the main problem, which in merge sort was n. Fn was equal to n in merge sort algorithm. So, whenever we are going to use divide and conquer strategy, the analysis of those algorithms will be done via this sort of a recurrence relation. The Master's theorem allows us to quickly write the solutions to this recurrence relation rather than working out by doing substitution or some other method. So, we will use them wherever they are going to occur. We are not going to look at the theorems, the proofs of this theorem. We are just going to be interested to use a particular case wherever it arrives or wherever it arises.